Okay. So let's write subproblem 1 more carefully. Suppose the sets B1, B2 up to Bk are given. That is, for each xn is this maximized? For each xn in the set D, we know the Gaussian density function used to sample xn, right? So the best way to understand this is that, remember, you had the switching problem. Let's say this is the data you want to sample xn, and you had a switch here. You had a Gaussian with mean mu1, covariance sigma 1, a Gaussian with mean mu2, covariance sigma 2, and a Gaussian with mu3 and covariance sigma 3. And we argued that these connections were probabilistic. With probability W1 you would go on the first branch, with probability W2 you go on the second branch, and probability W3 you go on the third branch. Once you go on one branch, you use the corresponding Gaussian to sample it, right? From this you get a xn as output. Now what we are going to tell you is that whether you went on the first branch, the second branch, or the third branch, this information is revealed. For every point in the training set, we actually tell you whether you went on the first branch or the second branch or the third branch beforehand. But we don't tell you what the rest of the parameters are. We don't tell you what W1, W2, this should be W3, what W3 are, what mu1, mu2, and mu3 are, and what sigma 1, sigma 2, and those things are not revealed to you. But we tell you during the sampling process at each time which branch was taken out of those three. That's what the sets B1 to Bk are. Is this clear? And your goal is to identify what Wj, μj, and sigma j are. So here we will use empirical means. As we discussed in this example, we will use empirical means or empirical estimates. So let the size, let Nj denote the size of Bj. So in this example, B1 tells you the number of points that were sampled using the first branch. B2 tells you the number of points that were sampled using the second branch. B3 tells you the number of points that were sampled using the third branch, right? That information is told to you. And your goal is to compute mu, sigma, and W. So let the size of B1 be N1, size of B2 be N2, size of B3 be N3, right? That we can count that because the sets are given to us. Then all you have to do is Wj will be Nj by N. This is the expected fraction of time you will land on the first branch, and j is 1, and so on. Mu j is 1 by n times nj times the summation of all xn in bj of xn. And sigma j is 1 by n j times summation of xn in bj of xn minus mu j times xn minus mu j transpose. Okay, these can be readily computed. This turns out to be the right thing to do, even from the maximum likelihood estimate point of view. We did not formally show this is the optimal choice. In terms of maximum likelihood estimation, it can be done, but I think it's very intuitive that this is the right thing to do. If you're given data points and you want to estimate what mean for the Gaussian is, take the empirical mean. Right? That will maximize the probability. For covariance, you will take the empirical covariance. Any questions about the notation, what the problem setup is, what we are doing here? Yeah?
Doesn't all this like assume you know everything? Like you have every single data point there is?
You have n data points here. What I don't understand.
And what I mean is like, what if like you want to identify something that's outside of this set of data that you have? Will this still apply?
So the setting is that you have n data points.
Yeah.
You assume your density function is a mixture of Gaussians. You know that there are k Gaussians. And you want to estimate the parameters of this density function, the wj's, μj's, and sigma j's, given this data set.
Yeah.
Once you have computed it, you can compute the probability assigned to new data points you have not seen from this function.
But you need a large enough n to generalize for other
You
points.
need a large enough n, so again that depends on k and n, so that's the classical question. But here we assume you have enough points so that you can train this generalizes reasonably well.
Okay.
I guess there is an issue with maximum likelihood estimate. That only works well if you have large number of points. So maximum likelihood is known to converge to the true density if you have sufficiently large training set. There are theoretical guarantees on a maximum. If you have small number of points, maximum likelihood is known to not be the right thing to do. There are variations of it. If you have 20 points, don't use the maximum likelihood estimate loss function. That's not good. There are variations of it, but generally you have enough points here, so we will stick to maximum likelihood. So any questions about this step 1? Is this easy? You will have exercises to do, like you will be using these function formulas in homework and so on. So if there is anything that is not clear, ask us. The covariance is this covariance matrix we had, right? It's this quantity, right? So this is, if you write it in matrix form, this is expected value of x minus mu times x minus mu transpose. This is the formula for the covariance. It's an outer product between x minus mu and x minus mu. We want to estimate this empirically. So what you do is instead, because you don't know how to px, you can compute this expectation. So we take an empirical estimate. We have x1, x2 up to xn, and we have just estimated the mean. So we use that. So this is what I wrote here is an empirical estimate of the covariance. You're averaging over the nj points that we have in this cluster. This is xn minus mu j times xn minus mu j transpose. Mu j was just computed here. That's the empirical mean. We plug that, and this is a formula that empirically estimates the covariance. I hope people are following. Okay, so we'll now move on to subproblem 2, which is what we introduced here. So here we reverse the question. Here we are given omega, which is wj, mu j, and sigma j. And we want to find the associations, right? So that is, for each xn in D, we want to find the density most likely to have generated xn. So in other words, again if we go back to the branching diagram, we had a Gaussian with mean mu1, covariance sigma 1. Say we have k equals 3 Gaussians. So in this setting, we know what mu1 sigma 1, mu2 sigma 2, mu3 sigma 3 are. That is known. We also know that we could select each branch probabilistically. So we know that we can select this branch with probability W1, this branch with probability W2, and this branch with probability W3. This is also given to us. There is a switch here which can select one out of these three branches with these probabilities. Okay? And we observe which xn was actually produced. We know the value of xn after this process was done. And the question we want to answer is it more likely, which of these three branches is most likely? Did xn take the first branch? Did xn take the second branch? Or did xn take the third branch? Right? So we don't know. We are given the input. We know that we are doing the switching here. We see what the value of xn was produced as the output. And we know all these values on each of the branches. We know what W1, W2, or W3 is. We know what mu1, mu2, mu3 is. We know what sigma 1, sigma 2, and sigma 3 is. And we want to know which path was actually taken. Did xn come from the first density? Did it come from the second density? Did it come from the third density? That is what we are interested in. We want to do it for each xn, and that's how we will construct the sets V1 to Bk. Right? So what we have is probability of, or f of p of xn, we have this. Given that the cluster equals j is a Gaussian with mean mu j and covariance sigma j. This is given to us now. If I know that I took the jth branch, then I know the density function that was responsible for sampling xn. Okay, this is given because the model parameters are given. I also know this. The probability of selecting the cluster J is Wj. Which path for any given data point, which path I take in this diagram. This is also given to us. Now, what I want to answer is, given I observe one particular xn, which path is most likely? Did I take this path, or this path? So how would you compute that quantity? Someone already answered that before, but let's see if people agree with it. So how would I compute which path is most likely? Yeah? So we have this, we have probability of xn given the cluster is j. And we have you multiply them together, but ideally what we want to do is we want to compute the following. We want to compute the posterior probability. So we want to compute the probability that the cluster equals j given xn. This is what is missing. This tells me how likely, if j is 1, how likely is it that I took the first path given that the output was xn. If j is 2, it tells me how likely the second path was taken. So that posterior probability gives me a probability of taking each of these three paths. And then I will choose one which has the highest probability and put xn in that particular cluster. So this can be computed. This can be computed from Bayes' rule. And so what this is p hat of xn given the cluster is j, probability that the cluster is j divided by p hat of xn. The numerator is known. This, since the model parameters are given, this is p hat of xn mu j sigma j, right? This is just that Gaussian times wj divided by p hat of xn. What is p hat of xn? How do I compute it? You sum it up, right? Summation of j going from 1 to n. So I have to compute this, which I can, because all the model parameters are given to me. I know what the wj's are. I know what mu j sigma j is. Xn is the data point I want to classify, so I have that as well. So I have everything here on the right hand side. And so what I do then is I just select, I say xn belongs to bj if j is argmax, say xn belongs to bj star if this is an argmax of this quantity of the posterior probability, right? So I will take j equals 1 and compute this. I will take j equals 2 and compute this, and j equals 3 and compute this when k is 3. And whichever one has a higher probability, I assign xn to that cluster. So if j equals 1 has the highest probability, xn belongs to b1. If xn has, if j equals 2 has the highest probability, xn belongs to b2, and so on. Any questions about this? So we have two sub-problems. One is that if we know which points belong to each cluster, which points were sampled from the first Gaussian, which points were sampled from the second Gaussian, and so on, we can find the model parameters easily. That was problem 1. This was the formula to do that, right? Instead, if we knew the model parameters and we want to find the clusters, that can also be done analytically. You compute the posterior and then you select the one with the highest posterior. So both the problems are easy. So let me just finish the second sub-problem on the next slide. So xn belongs to bj star if j is the argmax. If you look at this carefully, the denominator does not depend on j. So it's just a constant across all values of j. So you just have to maximize the numerator, which is the product as was pointed out before. So this is argmax wj times the Gaussian at mu j sigma j. So this is how the second sub-problem is solved. So both problems are easy. So how do we now put them together? You alternate between them. This is exactly the idea we had for k-means. So in the EM algorithm, and this is called hard decision version for reasons that will be clear shortly, you alternate between problem number 1 and 2. Okay. So you start with some arbitrary choice of b1, b2 up to bk. Then step 1 is given b1 to bk, use problem number 1 to find omega, which is wj, mu j, and sigma j. Step 2 is given omega you find B1 to Bk using problem number 2. And then you alternate between these two, alternate between step 1 and 2 until you reach convergence. The error stops increasing. That's the basic idea of the EM algorithm. EM is widely used in machine learning. This is just one application to the problem of Gaussian mixture models. But there are many areas in machine learning where they use EM algorithm. And the basic idea is that you decompose the problem into two simpler problems that have analytical solutions or very simple solutions, and you alternate between them until you reach convergence. That's the general principle of expectation maximization. So I'll write it on the next slide. Any questions? So you alternate, you any questions? Yeah? It's clear what the EM algorithm does. So it is notationally heavy because you have to understand the multivariate Gaussian densities and all that. But the intuition is fairly straightforward, I think. Good? Everyone done with this? So this is known as the hard decision EM. Because each xn only belongs to one cluster. At each point you force xn to belong to one cluster. You make a hard decision. In step 2, when you were to compute B1 to Bk, you force them to be disjoint, and you force each xn to either belong to B1, to B2, or to Bk. Now it could be that x1 has a 49% chance of belonging to B1 and 51% chance of belonging to B2 and 0% for everything else. Then you would still force xn to belong to B2, right? Even though it's almost equally likely to belong to B1 and B2. And this is not ideal. This is a suboptimal thing to do. And so this can be accounted for in the soft decision EM. So at each iteration, say t, let the fraction of xn belonging to the set Bj be denoted by gamma nj of t. So we say if we take n equals 1, then x1 we do not want to say it definitely belongs to cluster 1 or cluster 2 and so on. We say that a certain fraction of x1 belongs to cluster 1. That will be gamma 1 of t at iteration t. A certain fraction of x1 belongs to b2. That will be gamma 1 of t. Right? So all gamma nj's are positive. And if you sum them up for each we sum gamma and j across j, they should sum up to 1 because these are fractions of each point. So we are going to say certain fraction of the first data point belongs to cluster 1, certain fraction belongs to cluster 2, and so on. So if you sum each data point across all the k clusters, the sum will equal 1. Okay. So these are our auxiliary variables. We don't have B1, B2 as hard partitions. For each data point, we have these new auxiliary variables, gamma and j of t, which says how much of each data point belongs to the jth cluster. So this is what we introduce. Now, once we do that, the updates are actually pretty straightforward. So we can easily modify problem 1 and 2 for soft decision EM. We did the hard decision, but the soft decision version is actually not that complicated, right? So let me explain that. So let's look at step 2. So we'll first look at problem 2. Is anyone still writing this? Everyone okay with this? No? Okay. I have 10 minutes to finish it. It's 8:40. So 10 minutes to finish soft decision and we'll be done. Is the notation clear? Does everyone understand what gamma and j is? T is just the iteration index that we will use for simplicity. I will move on now. So still writing? Done? Everyone is done? Okay, so let's look at problem 2. Here, or actually let's look at problem 1 first. So here we are given gamma and j of t for each n and j. And we want to find omega, which is wj of t, mu j of t, and sigma j of t. We want to find the model parameters, right? Now in this case, what we will do is first we have to find the number of points in each cluster. Previously, you're just counting how many points belong to each cluster. In this case, for each point, we have a certain fraction that it belongs to cluster 1, certain fraction it belongs to cluster 2, and so on. So the right definition now is nj of t, the effective number of points in cluster j. This is just the summation of n going from 1 to capital N of gamma n comma j of t. So what this summation is doing is, let's say j is 1. We want to find the effective number of points in cluster 1. Then we'll look at what fraction of the first data points belongs to cluster 1, what fraction of the second data point belongs to cluster 1, and so on, and sum it up. So if 50% of the first point belongs to cluster 1, we'll have 0.5 in the first term. If 30% of the second point belongs to cluster 1, we'll have 0.3, and so on, right? We sum up the fraction of each point belonging to that cluster. That's the effective number of points that belong to that cluster J. Previously, if it was 0, 1, it was just counting the number of points. So this generalizes that definition. Is this clear? Then we compute mu j of t, which is now 1 over nj of t times summation of n going from 1 to n. We take the fraction of each point and multiply it by xn. So this is again doing sort of the empirical mean, but each data point gets multiplied by the fraction it contributes to that cluster. So previously this was 0 and 1, so we're only summing over points belonging to the jth cluster. Now for each point there's a certain contribution which is weighted by the amount it contributes to that cluster. So that's why we have gamma n j times x. Previously it was just summation over xn, where xn belongs to bj. So that time gamma n j was just 0 or 1. Now you have soft information, so you are going to multiply it by that fraction. So this is our empirical mean. And you're dividing again by the effective number of points. So this is again a direct generalization of the hard partition EM. Sigma j of t is again the empirical estimate, which is the same thing as before, but we have to account for the fraction. Okay. So again, dividing by the effective number of points in the jth cluster, taking the contribution of each point to the jth cluster and multiplying it by the associated estimate. So this is how you find omega in problem 1. Here you are given gamma and j's and you want to find omega, and again it's straightforward to do that. Just compute empirical mean and empirical covariance in a slightly different way where you weigh it by the fractions. Problem 2 is you are given omega and you want to update gamma and j of t. How will you do that? Any idea how to compute gamma and j given omega? So you are given now wj's, nu j's and sigma j's, and you want to find gamma and j. Any idea how you will do that? Well, you just have to compute the posteriors actually. You don't need to do any thresholding. So what you want to do now is you want to know how much of the nth point belongs to cluster J. So what fraction of the nth point belongs to cluster 1, what fraction of the nth point belongs to cluster 2, and so on. So again, gamma and j's are positive and they sum up to 1, right? So all you have to do here is we take gamma and j of t, or we are in the next step, so we are given the parameters, so that's why I had the t index. So I would do gamma and j of t plus 1 to be the probability that my cluster is j given xn. And this I can compute using Bayes' rule. So these fractions are nothing but the posterior probabilities. The probability that I see cluster 1 given xn, or I see cluster 2 given xn, and so on. So these are all positive values, they sum up to 1, and the fraction that 0.1 belongs to cluster 1 is simply the posterior. So here we are not throwing. In the hard partitioning, we are computing this, throwing away all the values except the one that had the highest probability, right? In this version, we don't throw away the posterior values. We keep all of them. And then we use that in the next update. Any questions about it? And then all you do is you just alternate between the two steps. So let me write it down and then we'll be done. So soft EM is initialize gamma and j of t in an arbitrary manner. Step 1 is given gamma and j of t. You update your model parameters. Step 2 is given omega. You update gamma and j of t, t plus 1 now. and you iterate between step 1 and 2 until convergence is reached. So this is the same EM algorithm, but the soft version, because you are keeping all the fractions into account. You don't make a hard decision for each point the cluster it belongs to. You keep the posterior probabilities as they are. It's the same idea, but slight tweak to account for the posteriors exactly. This is known to converge. This is guaranteed to converge. This version, the hard EM can sometimes oscillate. I believe there are no proof of convergence guarantees. Soft EM is guaranteed to converge to a local optimum. So if you can, you should always use a soft EM over the hard EM.
Did you just say local, not global? They'll converge to local.
This will always converge to a local optimum. You will never converge to global. None of these algorithms converge to global optimum because the loss function is non-convex. So this is it. We'll stop here. And next lecture, we will now move on to pack learning, the theory of machine learning. This completes the unsupervised learning part that we had to do.